All right, well, good morning, everybody. Nice to see people here and nice to see numbers appearing online of people who are tuning in, so that's good. All right, I'm going to ask you some top hat questions today, and the first one to answer correctly gets a free MacBook. No, I'm kidding. It's not actually going to happen. That is a computer for a master's student who's working with me, and this is a computer for a postdoc who is working with me doing computer security things. So, it's the latest and greatest in toys. Not to mention the fact that with another master's student, we're actually going out and buying a bunch of marine equipment that you would normally put on a boat just so that we can hack it and do fun things with it. So we're doing cool stuff. Yes, is it a question about starting a master's program in computer security? Because I'd love to answer that question. Yes?
Yes, you get free stuff.
Sort of. So these computers will remain university property, but on the other hand, when someone's done their degree, it's not like anybody really wants the computer back, so it's technically the university's property and they have to be able to return it, but I don't care if I don't know, it's complicated. I'm not actually 100% sure what's going on there. Previously I've said, yeah, I don't care, just keep it. And then somebody told me, you're not supposed to say that, and so I'm trying to figure out what to do. Anyway, that's a little bit beside the point, but hopefully my clever stalling tactic has allowed Top Hat to connect in this Firefox window, and it has not. So boo. Let's see. They're like Billy Crystal's character in Princess Bride, and he interrupts the thing where everyone's having a nice day and interrupts and says boo, boo. All right. Perhaps that is something that even people of a younger generation still get. We all love still the Princess Bride, right? There's like 3 cultural touchstones left that unite everybody, and one of them is the Princess Bride. Okay, that's good. All right. So today we are going to talk about, well, we're going to get real. We're going to have real talk today, in that we're going to talk about real numbers. Ching. Another thing that unites absolutely all of humanity is the disdain for the dad jokes coming from university professors. But oh well, such is life, I'm afraid. Something I would like to do here first, though, is indeed ask you one of these Top Hat questions. Oh, come on. It literally says, steeping some tea. Oh, thanks. That's super helpful. Okay, so let's see. We've got some questions that are coming in. Hello? Hello. Can we change our preferences now before May? Oh, that's an admissions question. Yes, the answer is yes. You can resubmit new preferences as often as you like until we close the form, and that'll be fine. And then we'll close the form on like the second day of classes, I guess, if in the spring semester. Regarding assignment 4, if our code passed all the tests in the auto-grader, does that guarantee a full mark on the assignment? Well, what do you think the answer to that question is? No, so I haven't released all of the tests. I'm actually going to post a couple of more tests before the thing is actually due, just to give you even more of a sense. But one thing that I have done, which I will mention here, let's see. EBGU, no, NG, 1020.ca. I will mention for the 4th assignment, I have posted, so I did encourage you, write some test code, like just write a module called tests.py, or a file called test.py, that just does things like import board and calls board.newBoard and see what result comes back, that sort of thing. I've given you an example of here's what some simple test code could look like, right? So my tests, it uses a framework, so it's a little more complex than this, but they do things like this. I import your code. I call board.newBoard, and whatever value you give me, I don't care if it's a list or an array or a dictionary or a tuple or whatever. It can be whatever representation makes sense to you, as long as when I pass it to board.pretty, that pretty prints the representation that you have. Now, that representation, if you want, it doesn't have to be very pretty. I have put no requirements on that, so that could just be you take it and pass it to the str function. So you take whatever your thing is and pass it to stir, and that'll give something. It won't give a very nice representation, it won't look like this, but that's okay. I'm not grading you on the prettiness of the representation that comes out of the pretty printing function. I'm going to take your board and Let's see. And I'm going to pass it into functions like count pieces. So whatever representation you gave me, I called new board. It created a new empty chessboard, empty meaning no pieces on it. Then I'm going to pass that into count pieces and say, okay, how many black pieces are there? How many white pieces? And the answer to both should be 0. And then here's some other examples of tests. Now I should mention, right now as things stand at this moment, if you submit 2 empty files to Gradescope, one called board.py and one called chess.py, you will score 3 points, like 3 out of 20, right? Just for empty files. If you create empty files that contain functions that do nothing, but the functions exist and they're called things like new board, count pieces, place piece, you will get a few more marks, right? So it's always a good idea when we're doing software development, don't try to solve all the problems in the entire world at once. Focus on one thing at a time, right? Create an empty file, upload that. Hey, you got 3 points. So if nothing else, you can lock in with that. Then create some empty functions and say, okay, I will come back and implement those later. Then think about, all right, now let me look at one of these functions at a time. How will I implement this? And if you implement 50% of what I ask you to do, you'll get better than 50% on the auto grader. And this kind of iterative, incremental approach is actually what we like to do in real software development. I never sit down and write 10,000 lines of code and then hope it works, right? No, I focus on one feature that I want. What's the first thing that I need? What's the most basic thing that I need to make this database system for tracking students' admissions preferences? What's the first thing that I need to make it do something useful? It's not going to replace the entire process that we have, but it'll do something that is useful. Okay, now that I've got that, how can I add to that? And then how can I add a little bit more? And that's what we do in real software development. So that's what you should do for these assignments that are getting a little bit more complicated. But like I said, there is this file here that you can download and you can run your code against this, and it will check a couple of things. It's not going to be an exhaustive test, but it will check a couple of things. And so that should be helpful for you. Also on the assignment, so a couple of people have asked me if this is going to be the last assignment, because originally the plan was to have 6, and obviously there isn't time left to have 6. So there's a bit of a sticky situation here, which is on the one hand, at this point I'm kind of not allowed to give you more assignments and tell me you have to do them, because we're in the last 2 weeks of classes. So if I wanted to give you an assignment that was due next week, I would have had to have given it to you last week. We're still working on assignment 4, so that obviously hasn't happened yet. On the other hand, there might be some people who are saying, boy, I didn't do so well on assignment 2 or something like that. If I had another one, it would really help me to bring my mark up. So what I think I'm going to do is release, possibly tonight, but tonight is already pretty full of other stuff, so maybe tomorrow. What I think is I'll release an optional assignment 5, which you will be able to submit, and if that is better than any of your existing marks, then it will replace your lowest assignment mark. So basically there'll be 5 assignments, but it'll be graded on a best 4 out of 5 basis. So that's something I think I can do, which doesn't get too far outside of the rules in that nobody has to do it, but if you want to, and if you were kind of counting on more assignments, then that's something that'll help you out. So that's what I'm thinking I'm going to do with respect to assignments. Let's see, for test 3.4, it's telling me I need a pawn in position A2, but I have one there. Okay, very specific questions about your particular assignment, things that I won't really address, with 118 people, but I will say, and I see that hand, I'll come back to it in just a sec. What I will say is that I do have my office hour today at 4. I'm going to have an extra office hour on Friday at 4. And depending on how we do with the course content and stuff, we might actually finish the lectures a little bit early. And so then maybe there'll be an opportunity, some slots may open up in my schedule where I could have a little bit of additional office hour type time if people were looking for that next week, or maybe even tutorials. So yeah, there are going to be some options there. I will have an office hour today. I'll have an extra one on Friday, and people can also, please do send me emails, and I try to respond to them as quickly as I can. Now, yes, there was a hand here. Yes. Yes, you will get the mark for assignment 4 before assignment 5 is due. You should have your mark for assignment 4 5 minutes after the deadline, basically, because it's all auto-graded. In fact, the tests that I'm not showing you yet, as long as they are there, then that mark will have been computed by the time the deadline comes. It's just the deadline comes and then the mark is released. Good. Let's see, will this still be due tomorrow since you have an extra office hour? My plan is currently to have that assignment still be due tomorrow. On the one hand, I'd kind of like to give extra time for people who might need that, but on the other hand, there are people who maybe arranged their schedule and didn't work on something else so that they could work on this. And so, I want them to have a reward for that, or at least not be penalized. So we'll see. If there is any extension, and at this point I'm not promising any, but if there is going to be any extension for assignment 4, there will have to be some kind of either a late penalty or alternatively some kind of a bonus for people who submit by the original deadline. So it's going to have to be something. If there is an extension, at the moment I'm not promising there will be. So, okay, hopefully that is helpful information. Right, I came into Top Hat not to look at the chat, although that's a good thing to do. I came into the Top Hat to ask you a question. So, here is a question. Thinking about this integer representation stuff that we were talking about yesterday, how do we represent the number 215 in a binary representation? While you're doing that, I'll take a moment to close this busted, useless tab over here. And then to realize that, as always, I'm showing you the wrong screen. Ta-da! So what's the binary representation of the number 215? And once again, that underscore 10 just means this is a decimal representation, a base 10 representation. Actually, it's kind of funny, the graduate student who's getting one of these computers is also TA in the course, and I actually just picked this up from Engineering Computing Services like 10 minutes ago, so he doesn't even know that this is in yet and ready for his use. So if he's watching the live stream, probably not. Most of the TAs aren't watching every stream, but if he was, then he'd get the good news that way. Maybe that's incentive for TAs to watch the live stream, because they do get computers now. All right, we're getting some answers here, so I'm going to close this out in just a moment. So let's close this question in 5, 4, 3, 2, 1, and a long one, and oh, look at that, just at the last second, boing, 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 some numbers pop up. All right, so let's take a look at the responses. So we had lots of different answers, and almost everybody said 11010111. As one robot said to another when they were telling a good joke or something. Oh, did you hear the one about the 11010111? So let us open our Thonny window and take a look at what that says. So 11010111 would be, if we kind of work in reverse order from the least significant to the most significant, that would be 1 plus 2 plus 4. And so let's be extremely explicit. 1 times 1 plus 1 times 2 plus 1 times 1 plus 1 times 2 plus 0 times 4 plus 1 times, 1 times 4 plus 1 times 8. Right, so once again, I'm working from the least significant to the most significant here. So 1 110, and then plus 1 times 16 plus 0 times 32 plus 1 times 64 plus 1 times 128. And that answer is 215. So, well done for everybody who answered 11010111. And some people were pretty darn close, but just missed the 32 in there, I think. All right, so that's good. So I'm glad that we understand this integer representation stuff, because it's going to be really important today as we get into some real talk, as in we're going to talk about real numbers. And I would say I'm sorry for the pun, but let's be honest, I'm not. So let's see. Oh, there's a question. If we have 5 assignments, do assignments overall carry 10% of the entire grade? So the assignment portion of the course will still be the percentage that was originally indicated, which was, I guess, 12%, which means that each one is just worth a little more now. So last time we talked about how a computer has memory, and that memory just stores bits, zeros and ones. When we put a bunch of those bits together, we call them bytes. So 8 bits are in a byte, and we use all of these bits to store integers. So a very common integer representation, for example, is to take 32 bits, which is 4 bytes, and that is a 32-bit number, which has a lowest possible value, if we're talking about an unsigned representation, of 0, and a maximum value just over 4 billion. So we can represent numbers that range from 0 to just over 4 billion. If you want to represent the number 5 billion, you can't do it in a 32-bit integer. And that's why, so computers have limitations in how we can express things like numbers. And so very often, in fact, those 32-bit numbers are used to represent not 0 to 4 billion, but we use a representation called a 2's complement representation, but we kind of use them to represent from negative 2 billion to about positive 2 billion. So if you've ever seen in a game, and I've seen this happen, if you've ever had a game in which you get when you get lots and lots of points, and then you get to the 2 billion mark, and then you add a little bit more, and then suddenly you've got negative 2 billion points, or in fact I've seen people do it the other way, where they play really badly in order to run their score into the ground, and they get negative 2 billion, then they do a little bit worse, and all of a sudden positive 2 billion. That's why. It's because an integer can only represent, a 32-bit integer can only represent numbers between either 0 and 4 billion-ish. It's actually 4 times 10 to the 24 to the power of 3, which is 2 to the 32. So you can only represent numbers between 0 and 4 billion, or negative 2 billion and positive 2 billion, approximately. And if you know that the number that represents your score, or the amount of money you have in a game or something, is represented in a 32-bit integer, then you can exploit that fact and make it wrap around and stuff, which is kind of fun. Yes?
What kind of games do you keep in
So games that I'm ashamed to admit that I played on a Palm Pilot while sitting in a chair in here instead of listening to Dr. Nefer or someone in first year. Don't do that. This is why I'm monopolizing your screens with Top Hat. See, it pops up stuff, and then, so I'm taking over your screens. But yes, hypothetically speaking, a game in which one was buying and selling substances for trade. Yes. Text-based gaming at its finest on the Palm Pilot version 3, which is good times. Yes, okay. And so the limitations of integers are really important. Today we're also going to see that computers are limited in how they can represent real numbers. Now, lots of numbers are actually represented with 64-bit numbers, which means the largest possible value is 2 to the 64, which is a mind-bogglingly huge number and works in almost any circumstances. Python's kind of neat because Python will transparently switch what kind of representation it uses as the integers get bigger and bigger and bigger. So if we're using integers that are smaller than 2 billion, it will use just a regular 32-bit number to represent that value. as we use larger and larger numbers, it'll automatically start to use more complicated ways of representing integers that use more and more bits and use arbitrary numbers of bits. And that's really important in fields like cryptography, something I care very much about, where we could use numbers that have hundreds of digits in them, because there are circumstances in which, for example, if you have two really, really large prime numbers, like hundreds of digits long large prime numbers, and you multiply them together and get another number, the fact that you know where that number came from allows you to do things that other people can't. And that's the foundation of a lot of kind of secure transactions on the internet. The fact that somebody who possesses a little bit of secret knowledge, which in this case is like where these two prime numbers created this other really big number, whoever possesses that secret knowledge can decrypt something, but other people can encrypt. And if you're more interested in that, I'd love to, because cryptography is a lot more than just the Caesar cipher. That's not really what we do in a contemporary sense. There's lots more to be learned about that stuff. Okay, so we talked about how integers are represented, and now we're gonna get real. We're gonna talk about real numbers. We're gonna talk about fixed point and floating point representations. Surprise! I went from integers to floating point numbers. I told you last time that would happen. And we're going to see how integers are still kind of the foundation even of a floating point representation. So the things that computers are really good at are following simple instructions, storing and manipulating integers. And that's about all that computers are really, really good at. And on top of that, we can build these amazing complicated systems that do all the cool stuff that you see here before you, mostly based on being able to do integer arithmetic and tell the computer to follow instructions. If this thing is equal to 0, run this instruction, otherwise do that. Okay, so we talked about integer representation, and we don't need to review it. We did a little question, that's okay. So how do we get decimal places? So we said that, and I wasn't thinking I was going to use my whiteboard app, but I think I actually will. So just one moment. Sorry. So with our integer representation, whether we're talking about a binary representation or any other kind of place value of number type representation, what is the significance of these different places? So the digits that we put in different places all have different values. Oh boy, she's slowing down now. Okay, so each of these places have a different value, and we saw that, for example, a ones place or a tens place or a hundreds place or a thousands place, that is 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, etc. In a binary representation, we're talking about 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, etc. But what if we wanted to represent smaller numbers? Like when I write the number 10.2, what does that mean? So we have 0, ones, we have 1, 10, we have 0, 100s, 0, 1000s. What's this? Yeah, so it's the base to the negative 1. So here we had b to the 0, b to the 1, b to the 2, b to the 3. Well, the decimal point means that after this, we have b to the negative 1. Right? This is the number of tenths. Then there's b to the negative 2, b to the negative 3. So the tenths place, the hundredths place, the thousandths place. Sorry, I'm trying to enunciate that very clearly to distinguish the thousands place from the thousandths place. So if we have 10.20, Well, it means that we have 2 tenths, 0 1/100ths, etc. So we can do this in decimal numbers, obviously, but we can also do this with other representations. So this is a thing that's called a fixed point representation. So if I said I've got 32 bits of integer, but I'm instead of making the least significant value be equal to ones, I'm going to make it be equal to 16ths or 32nds or 64ths or something like that. Then we have something that's called a fixed point representation, because we have a decimal point and we fix where it goes. So that decimal point would go in between this bit and that bit. So I could this is the problem with only having 2 hands. Much nicer if I had more hands. It sounds like the beginning of a superhero origin story, right? That's like how Doc Ock got started. He just wanted more hands to write on the chalkboard or something like that. So if we have a number like 11010111, hey, that's a number we had earlier, isn't it? I could say, hey, well, we have these 8 bits. I'm using those to store an integer, but I'm going to put a decimal point right there in the middle of it. So in that case, I still have a ones place, and a twos place, and a fours place, and an eighths place. But then I also have a 1/2 place, and a 1/4 place, and a 1/8 place, and a 1/16 place. And so this is a thing called a fixed point representation. So how much error could we have when trying to represent a number, a real number, using a fixed point representation? How far off could we get? Yeah, by a 32nd, because the smallest difference that we can have is a 16th in this representation, which means that anything that's going to be, anything will be rounded to a 16th, so anything will be within a 32nd of where we're trying to get. So if we say, well, that's not precise enough, I need more digits than that, then, well, we could shift where we want the decimal point. And we could say, all right, fine, well, here's a trade-off. Let's put the decimal point there, which means that now you have room for a 32nd. But what's the trade-off? What did we lose by doing that? Assuming that we still only have 8 bits to work with. Right, so now if there are more points on the right of the decimal point, there are fewer places on the left of the decimal point, which means that we can trade more precision after the decimal point at the cost of having fewer values that we can, or not being able to represent as large numbers overall because we have fewer bits available before the decimal point. Now this kind of a representation, this fixed point arithmetic, is actually something that is really important in things like machine learning and neural networking, and applying pre-trained neural network models to problems in order to do classification, because it turns out in a lot of circumstances actually we need floating point calculations, but they don't have to be super precise. We just need a lot of them to have been done previously. So in some cases a fixed point representation is actually a pretty good representation. But what's the problem with, imagine if I said, okay, you can, whenever you're going to write numbers from now on in Engineering 1, you can get within a 16th or a 128th of a value. You say, okay, that sounds pretty good under some circumstances. When is that not very good? Like, if we're talking about, you could put 6 decimals, you could have a decimal point and then 6 digits after it. If I said you could do that for all of your calculations that you do in Eng 1, that sounds pretty okay under what circumstances? Or alternatively, when would that not be very impressive to your physics instructor or your chemistry instructor, say? Right. Well, I mean, if you're talking about like chemistry, what is the mass of a uranium atom? It's pretty small, right? And so if we have those fixed point representations, if I told you you're allowed to use 10 digits before a decimal point and 10 digits after a decimal point, you might say, well, that's a whole lot of digits. Well, not when we're talking about things at like atomic scales. Or alternatively, how many atoms are in a kilogram of lead or something? A whole lot, right? A heck of a lot of atoms. And there's no way you could represent that with just 10 digits in front of the decimal point, right? So when we're talking about really big things or really small things, things that aren't around the value of like 1, that precision is not so impressive. So a fixed point representation is not so helpful. So when you do chemistry calculations and you're writing things in terms of like moles, do you tend to write, I have 0.000000000000926 grams of uranium? No, of course not. How do you write things instead? Right, so we use a scientific notation in which you might have something point, digit, 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 times 10 to the something, which allows us to represent really big numbers or really small numbers, and the precision that we have is relative to the size of the thing that we're talking about. So if we talk about significant figures, you might have a certain number of digits after the decimal point, but then that's scaled by that times 10 to the whatever. So if we're talking about really big numbers, then having 3 or 4 digits after a decimal point, you might still be talking about huge amounts of error. You might be talking about billions of atoms off. But if we're talking about 10 to the 23 atoms, maybe we don't really care about billions. Billions, that's just rounding errors. That's no big deal. And so that is not a fixed point representation. That is a floating point representation. And computers do this as well. So, oh, look at that. Now I've got these handy pictures that I'm going to show you instead of me drawing on my whiteboard app. Oh, well. So in a fixed point representation, we still just have an integer. It's just the whole integer is kind of like scaled up or scaled down by some multiplicative factor. We put a decimal point somewhere to say it's like you've got this integer, but divided by 16, or divided by 128, or divided by 256. That's kind of what it does when we put a decimal point in something, right? You could take a decimal point out of a value and just look at it as an integer, and then you could say, okay, but imagine that whole thing is divided by 100. And we do this in everyday life with things like dollars and cents. Right? Dollars and cents are a fixed point representation. We never spend fractions of pennies. Right? Things get rounded to the nearest penny. If you're spending cash these days, they get rounded to the nearest nickel. But things get spent to the nearest penny. So earlier in the course, at one point I asked, what would be a good way to represent money? What would be a good type? And a lot of people said, I guess a float would be a good type. And that's okay, because there is something after the decimal point. But actually, the best way to represent money would be with an integer. Just count the number of cents. And then if you want to know how many dollars you have, well, we just stick a decimal point in. We divide the whole thing by 100. And so that's an example of a fixed point representation that we use in daily life. Floating point representations are more like scientific notation. So we're used to scientific notation in lots of science courses that we're taking in Engineering 1, where there is some kind of a base raised to the power of an exponent, and then we multiply it by a thing. And that thing is sometimes called fraction, hence you'll see F. Sometimes people will call it a mantissa if they're being really, really pedantic and really picky about their terminology, which of course we all want to be, right? We love being really super picky about terminology. But we have a value like 6.02 times 10 to the 23. Well, in that case, 6.02 is our fractional component, or our mantissa, times 10 to the power of 23. So if we have a floating point representation where we say we're always going to have f times 2 to the e, then we only need to store the value of f and the value of e, and those two things together make up our floating point representation. So in scientific notation, we typically use a base of 10, and in the computer, because we love powers of 2, and we love the number 2 because zeros and ones, binary representation. So these things are typically a base of 2. So there's different ways we could represent floating point numbers, and you've got your choice of, well, how big can or what is your base? How big can your exponent be? How big can your mantissa be? There are two extremely widely used standards, and basically whenever anybody says floating point, they're talking about one of these IEEE standard floating point representations. So the IEEE, the Institute of Electrical and Electronics Engineers, is a body that, among other things, standardizes things like Wi-Fi. So IEEE 802.11 is the standard that describes how Wi-Fi should work and how everybody's kit needs to work together. My access point in your computer, or someone else's computer and someone else's access point, all these things work together because they follow a standard, and the IEEE does standardization. The IEEE also has member activities, and so there's an IEEE student branch on campus where they're building stuff and having fun together, and I'm the student branch counselor, so I'm happy to talk to people about IEEE membership too. But anyway, and so in the IEEE standard for how to represent floating point values, we store 3 things. So we store a bit that says, is this value positive or negative? We store an exponent, so it can be 2 to the something, and then we store this fraction. And we'll notice here that the exponent is an integer, so things can be times 2 to the 0, in which case it's just whatever the fractional value is, times 2 to the 1 in case it's twice that, or things like times 2 to the 256. That's a pretty big number, hey. So we can have the sign bit, the exponent, and then the fraction is stored as a fixed point representation. So we've got a 1/2 place, and a 1/4 place, and a 1/8 place, etc. And there are also, in the standard, it defines a couple of specific bit patterns that mean special values, such as infinity. So in Python, if we use the math module and we type math.inf, what you get is this special floating point value that is used to represent infinity. And infinity plus 3 is still equal to infinity. As well as that special value called nan, which is not nan and pop, but it is not a number. So we've seen that before. Well, it's actually implemented using a specific bit pattern in the IEEE standard that says whenever you see this pattern of bits, it means not a number. So there are 2 levels of precision in IEEE floating point. So there is single precision, which has 32 bits. And so we raise the exponent to 2 to the power of the exponent minus 127. So this allows us to have positive and negative exponents. So 2 to the 127 or 2 to the negative 100. So we can have really big numbers and really small numbers. And then the remaining bits, so there's a sign bit, there are exponent bits, and then there's 23 bits of this fraction or mantissa. So we get 8 bits of exponent. Now, if I had an 8-bit integer, oops, and I told you that its minimum value was 0, so 0, 0, 0, 0, 0, 0, 0, 0, that's 8. What is the maximum, that's 8 bits and its value is 0. What's the maximum possible integer that we could represent with 8 bits? With base 2, yep. Oh, that's close-ish. So, let me erase this. So, 2 ways to get at this answer. The slow way and the quick way. Let's do the slow way first. So if we've got 1, 1, 1, 1, 1, 1, 1, 1, that is 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus plus 128. Right? So if you add all those up, you're going to find that the answer is 255. The quicker way to do this is to note that, well, if we added 1 to that, then it would be this. Oops. So 2 to the 8 is 256. So it's 1 less than 256, which is 255. So 2 to the 8 is 256, 2 to the 9 is 512, 2 to the 10 is 1024. So the largest integer we could represent with 8 bits is 255. So the range of this exponent then, e minus 127, is from minus 127 to positive 128, which means that we can represent exponents of numbers which are as small as 2 to the negative 127. That's a pretty small number, right? In most calculations that we're ever going to care about, that's really small. And we can have 23 bits of fraction. So that fractional part uses that fixed point representation, and we assume that there's a prefix of 1. So it's implied that it's 1 point whatever this stuff is. So that's 1 plus base over 2, the bit over 2, the next bit over 4, the next bit over 8, the next bit over 16, the next bit over 32, etc. And 2 to the 23, that's a really small number. Yes?
Did you say that the biggest or smallest exponent we have?
So the biggest 8-bit integer that we can have is 255. But the exponent here is, because we want to also be able to represent small numbers and not just big numbers, the exponent, we subtract 127 from that value of e. So the exponent is anywhere between negative 127 and positive 128. So either really tiny numbers or really huge numbers. All right. And so this is how we compute that how we compute that fractional part. And we can get pretty precise. And between these two things, between the fractional part and the exponential part, we can represent really big numbers or really small numbers with quite a lot of precision and have very, very little error in how we represent them. But notice that the error is not 0. Right? There is error, it's just really small. It's on the order of 2 to the negative 24. That's a pretty small number, but it's not 0. And this is part of why we've seen when we do mathematical calculations and say, well, what is the sign of pi? Math module, it'll say the sign of pi is 0 point, or it's like 1 point something times 10 to the negative 16. And we say, well, that's a really, really small number. That is close enough to pi for almost any engineering application, but it's not 0, is it? And so if we were going to do lots and lots and lots of calculations based on these numbers, each of which has a small amount of error, those errors could add up. So we need to be aware of this fact. So single precision isn't precise enough for you. I mean, that's pretty precise, on the order of 2 to the negative 23. That's a lot of precision. But if that's not precise enough for your application, there's also IEEE double precision arithmetic, in which we use 64 bits, and this is, by the way, the default for all floating point calculations in Python and in a lot of programming languages. We use 64 bits in order to represent a huge number. So now our exponent can have 11 bits. So when we subtract 1023 from that, that allows us to have exponents that go from negative 1023. So you can represent a number that is smaller than 2 to the negative 123, which is really, really small, and it goes as large as 2 to the 1024, which is just a shockingly, unbelievably huge number. It's like more than all the leptons that will ever exist in the universe or something like that. Like, these are really, really big numbers that we're talking about. And also, the fraction now has 52 bits. So we can approximate a number that we need to reference with a precision of 2 to the negative 53. That is getting very, very close to of any value that we might care about. So that's why you'll sometimes hear the terms single precision and double precision numbers. And this graph here shows us that when we are storing a value that is close to 1, look at that. The single precision representation tells us that we can have an error of up to around 10 to the minus 7. That's still pretty close, right? That's more than the number of significant digits that we that we often care about in at least first-year engineering courses. Maybe when we get a little bit later into finite element analysis, we might care more about those things. But look, how much error can we have in a double precision floating point arithmetic representation? Well, it's somewhere close to 10 to the negative 16 when we're talking about a value that is close to 1. So that should sound a bit familiar because we've seen that level of error in things like computing the sine of pi. So for numbers that are close to 0, I mean, that's really close, right? That's pretty precise. For much bigger numbers, right, if we're storing a number which is 10 to the 12, then in a single precision floating point number, we might have error because we can't represent things that are within more than 10,000 of the quantity that we care about. But on the other hand, if we're talking about quadrillions, do we really care very much about thousands anymore? However, maybe we do. And so in a double precision floating point number, if we're representing a number that's in the quadrillions, the error might be more like in the thousandths, which is very precise indeed. And when we get into much smaller numbers, well, obviously the error is also much smaller. But the nice thing about a floating point representation is the precision, how precise you can be, varies, where the precision is much more precise for much tinier numbers, and it is less precise for big numbers, but for really big numbers we don't care as much. So this is why we use this to represent most real numbers most of the time in programming. And there is a pretty neat little tool here that we can use to visualize these things. There we go. So, like if we want to store a number like 2, you can see that we're able to represent the number 2 with actually just an exponent, and we don't need anything else. If I want to represent the number 3, you can see I can represent that using a bit here in the mantissa because it's 1.1/2 times 2 to the 1. So I can represent the number 3 exactly. If I want to represent the number 3.14, well, you can see I can get pretty close to it, but there is some error. So if I'm using single precision floating point numbers, which is what we're using here, you'll see that there is a little bit of error. So I can't represent the number 3.17 exactly using this representation. Now, I can represent it within 10 to the minus 7 of exactly the number, so that's not so bad, but you see there is some error. And so this is kind of a neat little tool that allows you to explore it. And also, this shows us what the bits would actually look like if you were just looking in the computer's memory. Notice there's nothing in those bits that indicates, hello, I'm a floating point number. In the computer's memory, it's just 32 bits. And you could look at those 32 bits and say, I wonder if that's a really big integer. I wonder if that's a floating point number. Well, what those bits mean depends on how you interpret them. And so sometimes this will be a thing that we have to worry about when you're looking at a dump of information in a computer's memory from a program that's crashed, and you're trying to figure out what was this. That looks like, yeah, that could be an integer that's in this range, which is related to this thing that we were working on in this program. Okay, maybe that's what that is. But the computer's memory doesn't say this chunk of memory is a floating point number. It just says, here are some bits. And then we have to interpret what they meant. All right, so that's fixed point representations and floating point representations. And that is how we generally represent real numbers in computing, using integers to make real numbers, or to represent real numbers. I'm going to post a couple more top hat questions of like review questions and stuff that people can use. Do remember that those practice quizzes are there. You do need to complete them to get the score of having completed them, but you can work on them together because they're top hat exercises. I will have my office hour this afternoon, and I will have an extra office hour on Friday, and beyond that, we will see each other again on Friday morning. So, until then, have a lovely day.